Safety integrity level determination is not a calculation exercise performed to justify an emergency shutdown system that has already been designed. It is a disciplined risk decision that answers one critical question: how reliable must a specific safety function be to reduce a defined hazardous scenario to a tolerable level? If you misunderstand that question, the entire functional safety process begins to drift. You may assign integrity levels to equipment instead of functions. You may credit safeguards that are not independent. You may inflate the required safety integrity level without improving the process design. Or, even worse, you may accept an apparently sophisticated shutdown system that cannot deliver the required risk reduction when the demand actually occurs. A safety instrumented function is a specific action intended to achieve or maintain a safe process state in response to a defined hazardous event. It normally consists of sensing, logic solving, and final element action. The safety integrity level is the reliability target assigned to that function. The function describes what must happen. The integrity level defines how dependably it must happen. That distinction matters. You do not assign a safety integrity level to an entire plant, control system, programmable logic controller, or shutdown panel. You determine the required integrity of each individual safety instrumented function against a clearly defined hazardous scenario. The process begins with hazard and risk analysis. You identify what can go wrong, why it can happen, what consequence can result, how frequently the initiating event may occur, which protection layers already exist, and what residual risk remains. Only then can you decide whether an additional safety instrumented function is required and what risk reduction it must provide. The objective is not zero risk. Zero risk is not a credible engineering target. The objective is to reduce risk to a tolerable level and then continue reducing it where further reduction is reasonably practicable. For low demand functions, the key measure is average probability of failure on demand. A safety integrity level 1 function typically provides a risk reduction factor between 10 and 100. Safety integrity level 2 provides approximately 100 to 1,000. Safety integrity level 3 provides approximately 1,000 to 10,000. Safety integrity level 4 extends beyond that range, but it is extremely demanding and rarely appropriate as the preferred solution in conventional process facilities. When a study appears to require safety integrity level 4, you should not treat that result as a design challenge for the instrument department. You should treat it as a warning that the process concept, inventory, operating conditions, layout, inherent safeguards, or protection philosophy may be fundamentally inadequate. The first response should be risk elimination, risk reduction through process design, or the use of multiple diverse and independent protection layers, not simply a more complex safety system. Demand mode must also be understood correctly. A low demand function is expected to operate no more than approximately once per year and no more than twice the proof test frequency. A high demand or continuous function is demanded more frequently, and its integrity is evaluated using dangerous failure frequency rather than average probability of failure on demand. Applying low demand calculations to a frequently demanded function can produce a dangerously misleading result. Good safety integrity level determination therefore begins with preparation, not with a workshop worksheet. The design must be sufficiently developed for the team to understand the process, challenge the operating intent, and evaluate the hazardous scenarios. Process flow diagrams, utility flow diagrams, piping and instrumentation diagrams, cause and effect diagrams, process descriptions, equipment layouts, control philosophies, shutdown philosophies, isolation philosophies, fire and gas philosophies, relief and blowdown philosophies, and previous hazard study records must be available and sufficiently mature. The hazard and operability study should normally be completed first. That study identifies deviations, causes, consequences, and existing safeguards. Safety integrity level determination then examines the hazardous scenarios requiring risk reduction and decides whether instrumented protection is necessary. Running the determination workshop before the hazard and operability study is complete is not efficiency. It is premature decision-making based on incomplete hazard information. A competent facilitator should be willing to postpone the workshop when the design, hazard analysis, risk criteria, or supporting documentation are inadequate. Proceeding with weak inputs does not save project time. It creates false confidence and transfers uncertainty into the safety requirement specification, verification calculations, procurement decisions, proof test procedures, and operating risk. The workshop must have a defined charter. The charter establishes the scope, systems to be reviewed, participants, responsibilities, schedule, methodology, and expected deliverables. Without a clear charter, the team can easily drift between hazard review, design review, control system troubleshooting, and integrity determination without completing any of them properly. The team must be multidisciplinary. You need process knowledge, operating experience, instrumentation and control competence, safety and risk expertise, project understanding and facilitation discipline. An experienced operator is essential because drawings describe intended operation, while operators understand actual operating behavior, abnormal conditions, startup difficulties, bypass practices, and the time realistically available for intervention. The facilitator should be competent, independent, and sufficiently detached from the original design. A designer naturally understands the design intent, but that same familiarity can produce confirmation bias. The facilitator must be able to question assumptions, challenge safeguard claims, prevent dominant personalities from controlling the decision, and keep the team focused on the scenario being assessed. The technical scribe is equally important. Safety integrity level decisions depend on assumptions, frequencies, consequence descriptions, safeguard credits, and team judgments. If those details are poorly recorded, the result cannot be reproduced, verified, or defended. Workshop records should be projected live so every participant can see what is being entered. That simple practice improves accuracy, exposes misunderstandings immediately, and converts the record into an agreed technical product rather than one person's interpretation after the meeting. For each candidate safety instrumented function, begin by establishing context. What equipment is being protected? What hazardous condition is being detected? What initiating causes can produce that condition? What final consequence is being prevented or mitigated? What action must occur? How quickly must it occur? What safe state must be achieved? Which existing safeguards genuinely act on the scenario? These questions force the team to define the function explicitly. A description such as high-pressure trip is inadequate. A functional description should identify the process condition, protected equipment, initiating scenario, sensing arrangement, required action, final elements, and intended safe state. The team must then ask whether an instrumented function is actually necessary. Before allocating risk reduction to a safety instrumented system, consider inherently safer design, inventory reduction, lower operating pressure, physical separation, mechanical protection, relief systems, process redesign, passive barriers, and other technologies. A safety instrumented function should not become the default answer to every unacceptable risk. Instrumented protection introduces life cycle obligations, independence, architecture, diagnostics, validation, proof testing, bypass control, maintenance competence, management of change, and periodic functional safety assessment. The principal determination methods are layer of protection analysis, calibrated risk matrices, and risk graphs. A qualitative method may be suitable for initial screening, but higher integrity requirements demand more rigorous analysis. When a matrix or risk graph produces a high integrity requirement, the scenario should generally be examined using a more transparent semi-quantitative method, such as layer of protection analysis. A risk matrix correlates consequence severity and event likelihood. It can be efficient, but only when calibrated to the organization's tolerable risk criteria and protection philosophy. A generic matrix copied from another company may look authoritative while producing decisions inconsistent with the actual corporate risk target. The matrix must evaluate the hazardous event without credit for the safety instrumented function being assessed. Existing safeguards may only be considered when they are dependable, verifiable, scenario-specific, and sufficiently independent. A risk graph uses consequence, exposure, possibility of avoiding the hazard, and demand frequency. It can be useful when numerical data are limited, but its categories and calibration factors must be defined carefully. Slightly different interpretations of exposure, avoidance, or demand rate can shift the integrity result significantly. Layer of protection analysis is often preferred because it makes the logic visible. You begin with a single impact event scenario, one cause, one hazardous progression, and one consequence path. Combining several causes or several consequences into one vague scenario destroys the calculation because different causes can have different frequencies and different safeguards. The initiating event frequency is estimated in events per year. Existing independent protection layers are then identified and assigned appropriate probability of failure on demand values. The word independent is non-negotiable. A safeguard is not an independent protection layer merely because it appears as a separate line on a cause and effect diagram. It must prevent or mitigate the scenario independently of the initiating cause and independently of other credited protection layers. It must be specific, auditable, dependable, and capable of performing within the available process safety time. Consider a high-pressure scenario caused by failure of a basic process control system loop. You cannot automatically credit another alarm or action using the same transmitter, controller, logic path, or final control element. Shared hardware, software, utilities, impulse lines, power supplies, communications, or maintenance practices can create common cause failure. Operator intervention may receive limited credit only when the alarm is independent, the operator receives a clear indication, the required response is defined, sufficient time is available, the operator is trained, the action is feasible under upset conditions, and the response can be audited and tested. Writing operator will respond is not a protection layer. It is an assumption until the alarm, response time, procedure, workload, human-machine interface, and final action have been demonstrated. Other conditional modifiers may include occupancy, ignition probability, fatality probability, vulnerability, escape probability, and environmental exposure. These factors must be applied consistently and only where they genuinely represent conditional probabilities in the event sequence. They must never be inserted merely to force the result toward a preferred integrity level. The intermediate event likelihood is calculated by multiplying the initiating event frequency by the failure probabilities of the applicable independent protection layers. Conditional modifiers are then applied as appropriate to estimate the mitigated consequence frequency. In simplified form, mitigated event frequency equals initiating event frequency multiplied by the probability of failure on demand of each credited protection layer multiplied by the applicable conditional modifiers. The result is compared with the tolerable frequency target for that consequence category. When the calculated frequency is already below the target, an additional safety instrumented function may not be required, although further reasonably practicable risk reduction should still be considered. When the calculated frequency exceeds the target, the ratio between the calculated frequency and the tolerable target defines the required additional risk reduction. That required risk reduction factor is then converted into the target probability of failure on demand and associated safety integrity level. Suppose the hazardous event frequency after existing protection layers is 1 event in 100 years, or 10 to the power of -2 per year. If the tolerable frequency is 1 event in 100,000 years, or 10 to the power of -5 per year, the additional function must provide a risk reduction factor of 1,000. That points towards safety integrity level 3 capabilities, subject to detailed verification and all applicable architectural and lifecycle requirements. But do not stop at the number. Ask whether the initiating frequency is credible. Ask whether any safeguard has been double counted. Ask whether the assumed protection layer shares equipment with the initiating cause. Ask whether the operator response time is realistic. Ask whether the final element can achieve the safe state before the process safety time expires. Ask whether the consequence severity reflects the actual inventory, occupancy, and escalation potential. The strongest workshop is not the one that produces the most precise spreadsheet. It is the one that exposes uncertainty before that uncertainty becomes embedded in the design. The same integrity determination logic may be extended to environmental and asset protection consequences. Environmental integrity levels and asset integrity levels can support structured decision-making, but they must remain clearly distinguished from personnel safety requirements. Commercial loss should not distort or dilute a safety decision, and safety integrity claims should not be inflated merely to protect production. Workshop duration must also be realistic. A complex function can require several hours to define and assess properly. Long, uninterrupted sessions degrade judgment. Fatigue encourages superficial agreement, repeated assumptions, and reduced challenge. Regular breaks, controlled daily duration, and disciplined action management are part of risk analysis quality. When information is missing, record an action. Do not manufacture certainty inside the meeting. Assign responsibility, define the required evidence, and prevent closure of the assessment until the issue is resolved. Every decision must be traceable. The record should identify the scenario, cause, consequence, severity, initiating frequency, credited protection layers, probability of failure on demand values, conditional modifiers, assumptions, tolerable risk criterion, calculated event frequency, required risk reduction, selected integrity level, actions, and participants. The final report should define the scope, methodology, team composition, systems examined, assumptions, data sources, results, recommendations, actions, attendance, and drawings used. It should be formally reviewed, approved, controlled, and archived. The report is not simply a workshop record. It becomes a design input. Its results feed the safety requirements specification. That specification must convert the integrity decision into implementable requirements: functional logic, trip settings, response time, voting architecture, failure action, reset philosophy, bypass controls, diagnostic requirements, environmental conditions, proof test interval, test coverage, maintenance constraints, and interfaces with other systems. And this is where many projects make a serious mistake. Determination does not prove that the design meets the target. Determination tells you what integrity is required. Verification demonstrates whether the proposed sensor, logic solver, and final element architecture can actually achieve it. Validation later confirms that the installed function performs the required action under the specified conditions. A function labeled Safety Integrity Level 2 is not automatically a Safety Integrity Level 2 function. The claim is only valid when the complete lifecycle evidence supports it. You must verify hardware reliability, architectural constraints, systematic capability, diagnostic coverage, proof test effectiveness, common cause factors, repair times, bypass exposure, and final element performance. In many practical systems, the final element dominates the probability of failure on demand. A sophisticated logic solver cannot compensate for an unreliable shutdown valve, poor actuator design, blocked impulse line, or ineffective proof test. The real discipline of safety integrity level determination is therefore not assigning numbers. It is resisting weak assumptions. Do not credit dependent safeguards. Do not use generic initiating frequencies without understanding the operating context. Do not assume an alarm guarantees operator action. Do not perform the study before the design and hazard analysis are ready. Do not combine unrelated scenarios to simplify the worksheet. Do not use a corporate risk matrix that has not been calibrated. Do not accept a high integrity requirement without first challenging the process design. Do not confuse determination with verification. And never allow the workshop record to become unreadable to someone who was not present. When the methodology is applied properly, safety integrity level determination becomes much more than a compliance activity. It exposes hidden dependencies, weak process safeguards, unrealistic operating assumptions, inadequate shutdown actions, and opportunities for inherently safer design. That is the real value. You are not assigning a label to a trip. You are defining the reliability of the last engineered barrier between a hazardous process condition and a consequence that the organization has declared unacceptable. Make that decision slowly enough to understand it, rigorously enough to defend it, and clearly enough that the engineers, operators, and maintainers who inherit the function can preserve its integrity throughout the life of the facility. File site, turn file 0.